Let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day, and I just thank you for this class and the opportunity we have just to meet together and study your creation and just enjoy the beautiful mathematics of Hilbert Spaces, Lord. In your name I pray, Lord Jesus. Amen. So let me continue on where we left off last time and look at these really, I think you'll appreciate them as we go on, why they're important examples. Because, this one, the Sobolev spaces one, it's a little bit more, I would say it's a little bit more adventurous. This one, example 3.37, here he's looking at, he defines L2, his notation is L2 with a row, AB. So these are complex valued measurable functions defined almost, let's see here, oh wait a minute, my bad. A space of all complex valued measurable functions on AB such that, so this is the terms and condition for being in this space, all right? F is an element of here. Means that the integral from A to B of the modulus of f of x squared times rho of x dx is finite. All right. Now, this rho of x, I think we usually call it a weight function. I mean, that's what I would tend to call it. It's a weight function. You could see the previous example we did before with basically having rho being equal to 1. The condition on rho is this. We need rho of x greater than 0 almost everywhere on AB. Okay, so that's the deal. It has to be mostly positive, maybe a few points of misbehavior, but all right. Man, my shoes are super squeaky today. Somebody spilled a cup of Gatorade up here or something. Anyway, so what's the norm in this context? So the norm here, excuse me, not norm, listen to me, we're in Hilbert space, right? Give it the program. So the inner product, we do f with g equals to integral from a to b. I bet it's complex, right? So there's probably a conjugate here. Yeah, f of x times g of x conjugate times rho of x dx, okay? All right, so there it is. That's the definition of the inner product. And so I will, let's take a look at his argument. So he says that this is a Hilbert space. So I won't bother with the uninteresting parts too much. I'll just talk about them. It's pretty clear that this is positive. For if you put f and f here, you've got an integral of f bar times rho. So that's like a norm f squared and times a positive function. Integrating a positive thing gives you back a positive thing. The only way that this, if you had f, the inner product of f and f being 0, you'd have the integral of a positive thing. Integral of the modulus of f squared times a positive thing equal to 0. So that would imply that f is equal to 0 almost everywhere. Which, remember, as I keep forgetting to point out, we're not working with functions, we're working with equivalence classes. There's always that we keep forgetting. I mean, we haven't talked about that, but it's still with us, right? Technically, we're working with equivalence classes of functions, up to the equivalence being the almost everywhere concept. Anyway, so enough about that. And you can prove the sesquilinearity follows almost immediately from this formula, right? Like linearity in the first slot and conjugate linearity in the second spot because of the conjugation here and the properties of the integral. So it's clear that it's every class, this is here. and I always forget to move it, and I just keep working around it, which is just dumb. Okay, so let's look at the completeness, though. That's a little bit more technical. So he says, to prove completeness, consider a Cauchy sequence. Cauchy sequence, Fn, in L2 row AB, all right. And he says, look at the norm of Fm minus Fn squared. And I don't want to write all this again, so I'm going to call this H. Okay, H. There we go. Well, that is equal to the integral, the absolute value of Fm of x minus Fn of x, right? Modulus of that squared times the weight function of x dx, right? Integral from a to b. And let's see, if that's a Cauchy sequence, that has to go to 0 as what? As n goes to infinity, right? For fixed m, yeah? This is one way of characterizing the Cauchy condition, is that you could fix one of the indices and limit the other one to infinity, and then that has to go to 0. Okay, so what he says is like define and I think this is actually a prototype for later arguments. Now I'm speculating a little bit, but I believe. Anyway, he's like, let big Fn be Fn times the square root of rho. All right, then what's the what's Fm minus Fn norm squared? Remember, this is the induced norm, right? The induced norm. Oh, so he's actually working in L2 at the moment. I mean, you can do that, right? Does that make sense, actually? What's the needed condition? F is Fn over rho, right? Big FF. What I'm trying to say is, if you plug this, if you solve this for Fn, right? And you think about plugging it into here, you get division by the rho squared. They cancel, and then you just have the integral of the modulus of the big F squared is less than infinity. In other words, this rescaling by that weight function is what you need for Fn to be an element of L2 AB. So this is something we can then calculate meaningfully. And that is just straight up the integral from a to b of the modulus of Fm of x minus Fn of x squared dx. No rho this time because we're just in L2. If you want to think of it, L2 is just with weight 1, you know. And then, okay, so then what? And then he just works it out and says, well, that's really just equal to, this is literally equal to, so basically, I'm not going to belabor it, but basically just plug this into here, pull the rho out, and you just get back to that again. I mean, I'm skipping a step or two, but basically, it's just you just pull the rho out. That the square root of squares to give you a rho, and bam. So what does this mean? This means that So it's simply this: if little fm is a Cauchy sequence in the row space, let's call it, in H, right? If that's a Cauchy sequence in H, then the corresponding scaled sequence, big F, is a Cauchy sequence in L2. But we already proved that L2 is complete. So thus, Fm converges in L2 AB, and I'm assuming that convergence in L2 will transfer to corresponding convergence in the row, in our row space as well, right? Yeah, so essentially it's just that. So then this means that you can make this as small as you want. There exists an F, all right, such that the L2 norm, right, and so if we let F equal to big F over rho, then you can argue that the Fn sequence converges to F in L2 rho AB. All right, so I think I've written enough that it's clear. So the idea is that, I mean, if you want me to get all fussy and stuff, for each epsilon greater than 0, there exists an n, sufficiently large such that when your, m is beyond that big N, this can be made less than epsilon. And because we can literally, take this equation essentially and divide by, more or less you can divide by the square, by rho and square root of rho squared. Anyway, so this pulls out a rho, right? And then you get, well, fine. I'll just, there's one equation here. So Fm of x minus f of x then, right, is equal to, what is equal to? It's equal to Fm of x times rho, square root of rho x, right? Minus, well, what's big F? Big F is f of x times rho x, yeah? Oh, my bad. See, that's not going to work. See, so I found a mistake. What should I have done? My limit, I'm trying to define the limit of our Cauchy sequence. And I was saying it would be the limit of the L2 sequence divided by rho. That didn't work, see? It's not going to work because what I want a square root here, right? So I should have divided by square root of rho to define the limit to the f to which our given Cauchy sequence limits. And so doing that will put a square root of rho x here, which is what we want, because then if you do the next step, you'll have Fm of x minus f of x, right? Squared times rho of x out here. And so basically you just feed this is equal to that, but then you tilt your head and you squint and you go, oh, wait a minute, but that's exactly the rho norm, which we can control because it's the same, it's equal to the norm which we already control. So, yeah. So there's that one. Let's see here. Next up, we've got the example of Sobolev spaces. All right, so here he's like, let omega be open subset of R big N, all right? And he says, watch this, let H tilde of omega, all right? I've missed an M, upper M, H upper M tilde of omega for M equal to 1, 2, 3, and so forth. Be the space of all complex valued functions so functions in, so Cm omega, what's that mean? It's more than continuous, right? And I don't, man, has he even talked about that in this book yet?
Yeah, I think he has.
He did? Oh, okay, cool. Because I was like, I don't remember that, but.
The derivative of order M is continuous.
Oh, okay, so yes, M continuous derivatives exist, all right. And here, context all partial derivatives up to order M. That's a lot of things, you know. Combinatorially, there's a lot going on there, you know, like when M is 1, you're talking about n partial derivatives, right? When n is 2, you're talking about, you know, the repeated partial derivatives, but you're also talking about all the mixed partial derivatives, right? So there's like, with increasing M, there's lots and lots and lots of possible partial derivatives you're talking about. If you think about it, there's a lot there. Algebraically, it's essentially the same animals like symmetric polynomials. But, okay, so complex valued functions such that, and then he says d upper alpha of f is an element of, what is it? An element of L2 omega. So what was that? That was the Lebesgue integrable functions on that open set of Rn, right? The things built by this on the terms of the step functions of the cubes in Rn, the end of chapter 2. So all that. So the multivariate, multi-dimensional integrable functions. And here, this is a very slick notation. Here, alpha is a multi-index. So it's for all alpha with the order of alpha less than or equal to m, where alpha is equal to alpha 1, alpha 2, dot, 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 dot. Well, what's his notation? Oh. Huh. What? I'll write it down. Maybe it'll make sense after I just think about it. I wasn't expecting that to be the same big N there. Fine. Alpha big N. Huh. I wasn't expecting that. Alpha 1 through alpha n are non-negative integers. I reject this. K. Where alpha 1 through alpha k are non-negative integers. Oh, I'm bad. Never mind, I see it now. I'll put the n back there. Okay, fine. Non-negative integers. and the order of alpha is equal to alpha 1 plus alpha 2 plus da 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 plus alpha n. And more than that, what do we mean by d alpha of f? Well, he's talking about the order alpha derivative of f with respect to partial x1, alpha 1, partial x2, alpha 2, da da da, partial. Okay, I see why he has to have n here. Okay, so fine. So my default way of thinking about things is to not list things that are 0. And so here, this notation, he's including, he says non-negative, right? He's being deliberate in that. Let's see if I can give an example. So if you're in like 4 dimensions, right? He could be looking at, say, the order of alpha equal to 3, and then he would have, you know, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 equal to, well, 3 in this case, right? And what that would mean, for example, if alpha was literally equal to, let's say 2, 0, 0, 1, then d alpha f would literally mean the, that's supposed to be partial, the third derivative of f with respect to what? Partial x1 squared partial x4. And the understanding is when you've got a 0 for that, it's not appearing. This is a very slick notation for a host of multivariate derivatives.
You said the alpha 1, alpha 2, but that alpha k are not negative, like you were saying. Would that, sorry that I put you with that. Yeah, no, I understand. Yeah, it's good.
So this is a very fancy way of saying you're allowing all derivatives up to order m. So like order 1 derivatives then in this index, if you have order 1, only one of these can be non-zero. Like one of them's 1 and the rest are 0. That's the first derivative. In the second derivative, when you get m equals to 2, you could have 2 of them are 1, and then you'd have like a mixed partial, or you could have 1 is 2 and the rest are 0, like the partial. And then when you get to 3, you could have like a triple mixed, or you could have a order 2 with an order 1, or you could have a simple just, you know, order 3. And this covers all of those different combinatorial cases all at once, this notation. It's very slick. Of course, you saw this in our multivariate analysis course here, which we don't offer, but I mean, well, that's only partly true. I mean, if I had not left and we had an advanced calculus going, then maybe that would be a different story for you. But oh well, I deserted you guys. But it's okay. I met Audric, so it's all good. Let's see here. Okay, so that is what that's what we mean. So we're saying this is the space of all functions that you can take up to m derivatives, m partial derivatives, and more than that, those partial derivatives are in fact Lebesgue integrable in this sense. All right, great. Okay, then what? So he's like, so you have you're basically imposing the condition, the integral over omega of these kind of partial derivatives, right? And of course, this is a complete list, right? If you're working in Rn, those are all your derivatives. You know, he's got everything covered there. So this has to be less than infinity. That's what it means for this. That's what this can, this right here, right, means that. Great. And that has to happen for every multi-index alpha of order less than m. And then how do you define the inner product? So, you know, inner product, how do you think we're going to define it? We define it like this. The inner product of f with g, it's going to be the integral over omega of the summation over all multi-indices, all multi-indices less than or equal to m of the derivative, multi-derivative, right, of f times the conjugate of the multi-derivative of g. And that will be the inner product. And I'm not going to write it out, but he gives you the stone cold formula for it in R2 on the next page. He writes it out. This is what this looks like. This is what this looks like in R2. It's really just, you know, at 0th order, it's just, so like at the start of it, I mean, I guess I could, you know, here's what this is, right? This is the integral over omega of, well, it's this, f times g bar, right? Plus dot, 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 plus let's see here how to say it. The mth, well, I guess I don't have a nice way to, I was hoping I had, I'll just leave it at that. Plus things. All right, so I mean, the derivatives, but he has it for n equals to 2 there. All right, so then what he says is he's like, okay, so this is indeed an inner product space. I think that's pretty easy to believe. Because of what? Because of the linearity of partial derivatives. Because partial derivatives are linear, and because the complex conjugate, you're taking the complex conjugate of something which is linear, so you're going to have additive, you're going to have linearity in the f slot, you're going to have conjugate linearity in the g slot. Because of the integral is linear, the sum is linear, the multi-derivative is linear, and it all works together to give you the needed, you know, sesquilinearity. And the complex conjugate pulling out, and the fact that this is equal to, like when you conjugate it, it's equal to, you know, the skew, this result, right? It's also relatively clear that if you had this, you get this. I mean, that's almost manifest from the formula. The positivity, if you look at it, you're going to have a sum of all of the derivatives, you know, I don't know, I'd have to think about why it forces f and g to both be 0 here. Because, well, I guess, okay, so you've got a sum of positive terms, right? So it forces the, if we put f and g both equal, we look at ff, like inner product ff, then you've got like, you know, f squared plus the derivative of f with itself squared of every possible kind of derivative squared, you know, it's like, you know, so since that integrates to 0, I suppose it follows then that the function has to be identically 0, because here's the thing, yeah, here's the argument. So if the function was not identically 0, then what would happen, since we have continuity, is it can't be non-zero at just one point, right? that means it has to be non-zero in a neighborhood of a point. But if it's non-zero in the neighborhood of a point, when you integrate f times f bar, it's going to give you a non-zero contribution, which then will contradict. So therefore, it can't be non-zero anywhere because of the continuity of f. I don't think I even need to get into the derivatives, honestly. But yeah. Okay, so great. And then he says this is an inner product space. However, it's not a Hilbert space because it's not complete. So this is, in fact, that's why he stuck the tilde on it. All right. So what can we do if the space is not complete? What can we do? Yeah, we can complete it. We can. So that's what we do. The completion of this space is denoted h m omega. So the completion of h tilde m omega is h m omega. And that is a complete inner product space, which means it's a Hilbert space. And he says this is a particular class of a general class, a particular case of a general class of spaces denoted. So this is a subcase of, here's the general notation, W m comma p omega. All right, I'm assuming the p is equal to, yeah, p is equal to 2 and m is m. Okay. So all of this is due to Sergei Lvovich Sobolev. 1908 to 1989. I think 1989 is the year it started to become clear that baseball cards were a bad investment. That's my own personal meaning for 1989, but should have sold them right then. Oh well, it's too late. But all right, so page flipped. All right, so let me move on here. So this is a very important class of spaces for studying partial differential equations. Like, this is the home of the analysis for partial differential equations, a good chunk of it. Not that I'm an expert, by the way. Partial differential equations is something that keeps coming up for me, and I'd like to know more about it, but I've always attacked it on the ground where it comes to me. Like, I never felt like I had a full treatment of partial differential equations in a course. I haven't had a dedicated analysis course in partial. I mean, I had a course as an undergraduate which was on solving partial differential equations, and I'll show you things I learned in there and here as we go on. We will soon hit on things that I will show you examples of concrete calculations. So, yeah, like partial differential equations is, that's such a big part of the story of physics and engineering and applied calculus. Like, it's unfortunate we don't have a class here. Okay, so now he's going to define strong convergence and weak convergence. All right, so let's do that. All right, so strong convergence. Strong convergence, weak convergence. So strong convergence is going to be basically a sequence xn in Hilbert space is strongly convergent I mean, I just wrote it. I don't need to write it again, dummy. So, oh, I do, curses, is strongly convergent to X. Goodness gracious. If you have the norm of xn minus x goes to 0, and then goes to infinity. And what norm are we talking about? We're talking about this one, right? The norm of x is the square root of the inner product of x of x, right? Okay, so the induced norm, right? That's strong convergence. Weak convergence is weak. It's weakly convergent to x. Weakly convergent to x in E. All right, the Hilbert space is equal to E. All right. If here it is, the inner product of xn with y goes to the inner product of x with y as n goes to infinity. All right, for every y in E. So weak convergence concerns the inner product, whereas strong convergence is our typical, usual notion of convergence for a norm. All right. So what would you like to say? Should strong imply weak? Probably, right? So the first theorem here is that a strongly convergent sequence is weakly convergent, and in fact to the same limit. So, and also notation, this is summarized by writing xn goes to x with a w over it. Weak convergence. All right, so here's the theorem. If xn goes to x, then xn weakly goes to x as well. And here the context, of course, is a sequence in the Hilbert space. Yeah. All right, so the proof, he says, is basically by Schwarz's inequality. So let me write it down here. He looks at the absolute value of xn minus x with y. All right. We'd like to get control over that. I think that would be pretty much what we need. Well, anyway, that's going to have something to do with what we're interested in for sure. What's the Cauchy-Schwarz inequality say? This is what, less than or equal to what? Mm-hmm. So let's see here. So if we, basically, if I let epsilon be greater than 0, I can choose, m sufficiently large, right? Such that the norm of xn minus x, right, is less than epsilon over the norm of y. And then if I look at the absolute value of xn and y minus the inner product of x and y, then by linearity in the first slot, that's literally equal to this, right? That's the additivity in the first, yeah. And then of course, this by Cauchy-Schwarz is less than or equal to norm of xn minus x times norm of y, which by construction is less than epsilon over norm of y times norm of y, which is of course equal to epsilon. So therefore, thus, the limit as n goes to infinity, right, of xn comma y is equal to xy. So xn weakly converges to y, to x rather, which is the theorem. Now, of course, there is a gap in my current argument. We're supposed to show that this is true for all y, right? My current argument only shows it for y not equal to 0. Right? So how do I get this limit is also true for y equals to 0? So like set y equal to 0 here, right? Set y equal to 0 here, what happens? Is that true? Is the equation true in that context? My argument fails. My argument, right, my argument fails in that case, but this is the exceptional case, and it's not a big deal because when you take the inner product of with 0, remember that's whenever property inner product with 0, 0, both sides, so woohoo! The limit of the 0 sequence is 0 as well. That's also at play here, not that it's interesting, but yeah. So that's that. Next theorem. The next theorem is that if xn goes to x and yn goes to y, what do you think happens? So you've got xn goes to x, yn goes to y. Put these two things together, you get that the inner product of xn with yn goes to xy. So let me prove this one, if it's not too hard. I only do easy proofs in here, you know. That's all you guys pay me for. No. I'm just kidding. It's mostly because physics has worn me out, as I was telling you. Okay, so he's going to look at the difference of this one and that. And so how does he look at that? Well, he does something sneaky. He adds 0 in the middle, x with yn. So I'm going to go straight to the step beyond the step that I'm thinking about, because I mean, he basically subtracts x with yn, right? And then he adds it. And then after that, he does the triangle inequality. So basically add 0, apply triangle inequality like that. Oh yeah, thank you. Still in the marker, there we go. And of course then that is you know, xn minus x comma yn. And then here you've got xn, you've got x with yn minus y. Remember, we proved that even though it's complex, it's conjugate linear, it's still additive, it's still the difference, the additivity still works in the second slot as long as you don't try to do anything with complex numbers. Minus 1 still works like normal, so even in the complex case.
In this case also, that would be equal to the conjugate of 1 not minus y x, but
oh,
the conjugate of
true.
itself, right? So we just do
That is true. Yeah, you could also conjugate the problem away, and then.
But
yeah. That's a good other way to think of it. And then what? Oh, so then. So this is less than or equal to norm of xn minus x times the norm of yn plus the norm of x times the norm of yn minus y. And the thing is, Well, let me explain the reasons. I don't actually want to do the epsilon argument explicitly this time. I'm just going to explain to you why we could. We have control over this given these limits because we can make this and that, I'll underline them in blue, we can make these norms as small as we like because we're given these convergence. Furthermore, if a sequence is convergent, it's bounded.
Right, yeah.
So since the sequence is convergent, it's bound. So this is bounded.
Right, yeah.
And well, this is just a number.
Right, yeah.
So that means that we can make an appropriate, you know.
Epsilon would be epsilon.
Yeah, epsilon. Yeah, the minimum of like,
Yeah.
or the maximum because we're in the ends. So like the
maximum. I'm sorry, with the maximum 2 will give us the smallest.
yeah, so you want like the maximum of the one that gives you, like you said, epsilon over 2 times the bound for this piece, and then epsilon over 2 times the norm of x for this piece. And then I guess probably in the case that x is equal to 0, it's easier, right? In the case that y is the 0 sequence, it's also easier. So those are,
So we don't have to go with that.
or I guess if the bound is, I mean, well, anyway, if 0 is,
It would just be the x rejected for that.
Yeah,
We
yeah.
got the bound already.
yeah, yeah.
Yeah. Right.
So that's that. And he says an immediate consequence of this theorem is that, so he said corollary, xn goes to x implies that the norm of xn goes to the norm of x. So do you see why that is? Basically, you just put you put xn equal to yn, so you've got, you know, this is xn, right? Which goes to square root of xx by the theorem, which of course is norm of x. So like that's the proof of the corollary. Theorem 13. All right, so I think, yeah, well, I guess I'll erase Mr. Sobolev. So we write down the theorems that remain in this section. I enjoy the proofs of these theorems, but we probably should go on. Theorem 3.3.13. This one says that if xn weakly converges to x, and the norm of xn converges to the norm of x. Now that's not convergence. Understand, that's not convergence in a Hilbert space. That's convergence in the complex number system. Or actually the reals, because it's a norm. Then what? Then that's actually enough to get xn converges to x. In other words, weak convergence plus convergence of the norm implies strong convergence. That's what this is saying. Let's see here. And then theorem 14 is if you have S subset of inner product space E such that the span of S, what's the span, by the way? I'll write it out. It's the sum, let's say I equals 1 to n of Ci, I'll say Si, such that, you know, Si is an element of S and n is an element of the natural numbers. So it's all possible all possible finite linear combinations of elements of S. Oh, I didn't finish the thought here. Is dense. Ooh. Dense in E. All right, so that's interesting. If xn is bounded sequence in E, all right, and xn comma y goes to xy for every y in S. Aha. Then xn weakly converges to X. So what this is saying is that essentially weak convergence with respect to a dense subset, it's not even that. Weak convergence with respect to a subset whose span is dense. Right? Like, notice that S could be a finite set here. I mean, because in the plane you have two vectors, right? You take their span, it's the whole plane. Is the whole plane dense in the plane? Well, yeah. So I think this becomes more sneaky in infinite dimensions, probably. But this is weakening the weak. It's weakening the weak convergence to just drop us down to a spanning set. And not even a spanning, it's not even a spanning set for E, right? It's if the completion of the spanning set is all of E, that's, yeah. Let me see here. So, and then the, let's see here. The theorem, the proof there, it's an epsilon over 3 proof. And it's interesting. It reminds me of the other epsilon over 3 proof is like the theorem about like a sequence of uniformly continuous functions. I think like the limit function has to be continuous. Remember right? Anyway, let me go on here. So theorem, I'm going to skip that proof. Not that it's too hard for us. I just, something has to give. 3.15. Weakly convergent sequences in a Hilbert space are bounded. Weakly convergent sequences in Hilbert space are bounded. That is, if xn is a weakly convergent sequence, then there exists a number m such that, all right, so if xn, let me say it this way, if xn goes to x weakly, all right, then there exists m greater than 0 such that the norm of xn is less than or equal to m for all n in the natural numbers. So that's the bounding he means. Right. I think I have time to prove that one. Let's do that. So, let's see here. I guess I can do the proof. I'll do the proof up here, so you can keep it there. It's cool. Sorry, Mr. Sobolev, you got to go. All right, so here's the proof. He says, let Xn be a weakly convergent sequence in Hilbert space H. Define, all right. So let's suppose Xn weakly converges to X. Define f sub n of X equal to X with an inner product of X with Xn, all right, for n in the natural numbers. All right. He says then Fn, if you look at it, is a mapping from the Hilbert space, all right, to the complex numbers. And he says it is a bounded linear functional. It's a bounded linear functional. Why is it bounded?
Something about bounded. Is it, I don't know if you prove something like this, but is it that bounded says bounded? That one makes sense.
He says it's by theorem 3.3.11, which I think is one we proved earlier. That's that the strong convergent implies weak convergent. How? Wait, what? Hold on a second here. But wait a minute. So we got to think about what we're proving. We're assuming what? We're assuming that. Oh no, we're not assuming it's bounded. That's what we're trying to prove, right? Weakly convergent.
Oh, yeah. Oh, sorry. Yeah, it's bounded. Okay.
He's probably going to argue it. Like, probably he's making a claim in this sentence. This is usually what happens when I read a sentence and it doesn't make any sense. It's because that sentence is a claim.
Yeah.
So let's hope for that. Probably the next paragraph establishes this. Let's hope for that. All right. He says, okay, since for every x in H, the sequence xn converges. Is that true? Oh, yeah. So by weak convergence, right? By xn weakly converges to x, we have that, how's this go? I've forgotten my definition of weak convergence already. Xn with x goes to xy, right? So that actually, we've got xn, we've got x, good grief, xn goes to xx, right? But of course that's equal to the norm of x squared.
Well, x and x goes to x. Or where?
Who?
X and x goes to x next with that matter. Well, I guess, where that from? They're all real.
Oh, you're saying that the definition of weak convergence got the xn on the other side?
Yeah.
Oh. Oh, yeah. Fair enough. All right.
How do I think